Now we're going to look at mathematical induction. This is the beginning of chapter 5, section 5.1. Now, let me compare it to a simple situation. We know that we can count up to numbers in the millions or even billions if you wanted to, because we know where the counting numbers start. They start at the number 1. And if we know a particular number that we're on, then we can think of the next number. For example, if we were on 4,356, we know that the next number is 4,357. Then 4,358, 4,359, and we know what comes after 59. It's 60, so it'll be 4,360. So as long as we know the rules of how to get the next number, we know we can count to however high we want. Okay, that's similar to the principle of mathematical induction. Now, Rosen uses this ladder illustration, as you see on the slide. He says we need to show that you can reach the first step, that we can reach the first step. And then he says, show that if we can reach the k step, the step number k, then we can also reach step number k plus 1. All right? So all we have to have is those two things, that we can reach the first step, and then if we can reach the kth step, then we can reach the k plus 1th step. If we know both of those facts, and the second one is an if-then statement. If we can assume we can reach the kth step, then we can know we can reach the k plus 1th step. So if you have both of those facts, we know that we can reach the whole staircase or whole ladder. Okay? Because, you know, if you're on step 1 and you apply that second principle, well, that will get you to step 2. And then if you are on step 2 and apply this second principle, you can get to step 3, and on and on up the ladder. Okay? Now, let's look at the principle of mathematical induction as it applies to a proof in mathematics. That's what we're trying to get to here, is the ability to use this method as a way to prove something in math or in computer science. So if you look at the top of the slide, it says principle of mathematical induction. It's used to prove that P of n is true for all positive integers n, where P of n is a propositional function. So it's some proposition that we're trying to prove is true for all positive integers. So we do 2 steps. We do 2 steps in this mathematical induction method. First, we show that we could reach step number 1. Okay, now this is called the basis step. And we show a proposition holds for n equals 1, usually by just plugging in 1 for n into the formula. So this step is pretty easy. We just plug in our initial value and make sure the formula works. Second step says that if we can reach step number k, then we can reach step number k plus 1. All right. Now, in the induction step, it's called, the second step is called the induction step, we prove that if we can assume the proposition holds for n equals k, so we'll assume it works for k, then we have to show or prove that will also hold for n equals k plus 1. Okay? And we'll show some examples how we do this. All right. Now, if you love concise symbolism, this could be expressed as the following conditional statement. Now, you notice the arrow here is a conditional. And then there's one big parenthesis around all of this. All right, so this says P of 1. In other words, it works for the first case. And then that symbol is and, so it works for the first case. And for all k, if P of k also gives you P of k plus 1. So if it works for the kth term, then we also know that it works for the k plus 1th term. Those two facts together imply that for all n, P of n holds true. An example, or some examples of mathematical induction. I'm going to start with a relatively easy to understand example involving a summation. So let's look at that. Now, consider the following sums of the first n positive odd integers. Okay? Now, we're adding up the odd integers, but we're going to look at one odd integer, or two odd integers, or three odd integers, or four odd integers, adding up that many of odd integers. Okay? So when we add up the first one odd integer, well, that's just the number 1. You only have 1 to add up. So the sum of the first one odd integer is just 1. Now, if you have two odd integers, well, that would be 1 plus 3, because those are the first two odd integers. That adds up to 4. When you add the first three odd integers, okay, 1 plus 3 plus 5, that adds up to 9. When you have the first four odd integers, 1 plus 3 plus 5 plus 7, that adds up to 16. When you add the first 5 odd integers, you get 25. And when you add the first 6 odd integers, it adds up to 36. Now look at these numbers that we resulted in. 1, 4, 9, 16, 25, and 35. Or 36, excuse me, 36. What do you notice about those numbers? Do you recognize that sequence of numbers? 1, 4, 9, 16, 25, 36. Well, I don't know about you, but I recognize that sequence of numbers, which would keep going, and the next one would be 49, and the next one after that would be 64, and then 81, and then 100. These are the perfect square numbers, okay? So if I was to write and fill in the blank here, it would be basically n squared. All right, it's the square of n. And you'll notice that if you look at this, we square 2, we get 4. We square 3, we get 9. We square 4, we get 16. We square 5, we get 25. We get square 6, we get 36. So it's just n squared. So what we think is true is this right here. Show that 1 plus 3 plus 5 plus ... all the way to 2n minus 1, which is like the stopping number, the nth odd integer, and you add that all up and you get n squared. So we believe that that's what the correct formula is. All right. Now, the first step of mathematical induction is to show that it works when n is 1. Okay? Now, that means when you have just one odd integer, which of course we already know was 1 equal, that sum was 1. Now, does it work when I plug 1 into this right side? 1 squared, yes, of course. 1 squared is 1. So the formula works. Okay? This step is generally very easy. You just plug in 1. Now, some students get confused because the formula has a bunch of these, like 1 plus 3 plus 5 plus dot 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 all the way to 2n minus 1. But when you're using the formula for the first one or two, or 1, 2, or 3 values of n, you don't necessarily have all those terms that are listed. Because like I said, in the first case, when n is 1, we only have one term. When n is 2, we only have 2 terms. When n is 3, we only have 3. So we won't have all of these that are in the formula necessarily. Now notice that when you plug in 1, 2 times 1 minus 1, that's 1. So that's your stopping number. So we had to start at 1 and stop at 1. So that's why we only had one term. All right, moving on. Now, step 2 of this process says, show that if we assume that 1 plus 3 plus 5 plus dot 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 all the way to 2n minus 1 equals n squared is true for k. In other words, we're going to plug k in there, and that'll be our inductive assumption or hypothesis. Then it'll also work for k plus 1. All right, so here's the proof of the induction step. Assume that 1 plus 3 plus 5 plus dot 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 all the way to 2k minus 1. Now notice I plugged k in where the n used to be. I'm assuming it works for k. So I stick k in for n. And then the right side is n squared. So you plug it in for k, it'd be just k squared. Okay? So that's our inductive hypothesis or assumption. All right, now to get that it works for n plus 1, we have to have another term added to this, right? You're adding up the terms up to the kth term. To get to the k plus 1th term, we got to have the k plus 1th term added in there. So that's what we did here, is we add the k plus 1th term to both sides. So I added it here. Now, the k plus 1th term means that I'm going to plug in k plus 1 for n. And so I showed that right here. 2 times k plus 1 minus 1 is the next term when n is k plus 1. But I have to add that to both sides. Okay, of course, what you do to one side of an algebra equation, you got to do to the other side. So that's what I did. I added the k plus 1th term to both sides. Okay. Now, if you distribute the 2 to the bracket, so you get 2k plus 2, but then you have the minus 1. So 2k plus 2 minus 1 is just 2k plus 1. All right. So that was added to the k squared that we had on the right side. Okay. Now, what we have to do is get the whole thing to be this formula, but with k plus 1 plugged in instead of the n. So I need to have k plus 1 plugged in for n. And very easily, you see that we can just factor the k squared plus 2k plus 1. How does that factor? Well, that factors to k plus 1 times k plus 1, and k plus 1 times k plus 1 is just k plus 1 squared. So just using algebra, we added the k plus 1 term to both sides. We did a little bit of algebra to simplify that, and then we factored and got k plus 1 squared on the right side like we wanted. Now, why did we want that? Well, that is the k plus 1th step. Okay, so what did we do? We started with the assumption that it works for k, which is in the first line of the proof of this step, and showed that it would then also work for the k plus 1th step. Okay, and thus, by the principle of mathematical induction, that we know for all positive integers, it will be true. All positive integers n the sum of the odd numbers of n odd numbers would be n squared. Okay, so if we wanted to know what's the sum of the first 100 odd integers, well, that would be just 100 squared, or was it 10,000? So the sum of the first 100 integers is 10,000. Now, we can also use the mathematical induction to prove a proposition holds for n equals 0, and then 1, 2, 3, 4, etc. In other words, we don't always have to start at 1. We could start at 0 as your starting value. Or we could start at some other starting value. We don't always have to start at 1, but we would have to prove the basis step, step 1, the n equals 0 case, or the n equals b, whatever the starting value b, or it's called the base case, whatever that is, we'd have to show that it works for that. All right, so study this example, and that's similar to some of the examples that you'll have to do in the homework. Now, let's look at Rosen's example number 3. Okay, so this one is a little different because it involves exponents, but it's not something out of the real strange and difficult. Rosen's example 3 says use mathematical induction to show that the sum 1 plus 2 plus 2 squared plus 2 to the third plus 2 to the fourth all the way to 2 to the nth power for whatever value of n we want is equal to 2 to the power of n plus 1 minus 1. Okay? Like, for example, if we had n equal to 3, then we would add up 1 plus 2 squared all the way to 2 to the third power. So what's 1 plus 2? Well, that's 3 plus 4 is 7. 7 added with 8 is 15. Now 15, it does equal 2 to the 3 plus 1, or fourth power, minus 1, because 2 to the fourth power is 16, and 16 minus 1 does equal 15. So it works for n equal to 3, but how do you know it continues to work no matter how high you want to go? That's what mathematical induction can do, is prove it works for all numbers. In this case, we're going to start at 0. N is greater than or equal to 0. So 0 is our starting place. So our basis step would be P of 0 is shown to be true because 2 to the 0 equals 2 to the 0 plus 1 minus 1. We're just plugging in 0 for n here. And 2 to the 0 is equal to 1. And 2 to the 0 plus 1, well, that would be 2 to the first power. And 2 to the first power is 2. And then you'll have 2 minus 1. But 2 minus 1 is equal to 1. So it works when p is, or when n is 0. So the proposition holds when n is 0. So now we assume that it works for the kth term. So I basically plug in k for n. So I have 1 plus 2 squared plus all the way to 2 to the kth power. And that should equal 2 to the k plus 1 minus 1, which is what I have here. All right. Now we're going to add the k plus 1th term to both sides of the equation. And that's what I did on the right, in red, in the color red. So I've added 2 to the k plus 1 on the left side and 2 to the k plus 1 on the right side. Okay? So on the left side, we are done. We don't have to do anything with the left side because this shows the left side going from 1 all the way to the k plus 1th term. 2 to the k plus 1 would be the k plus 1th term. Okay? So all we have to do, though, is get the right side to look like what it should be, where n is k plus 1. But of course, right now, we don't have that. If you look at this, we have 3 terms instead of just 2 terms like the right side is supposed to have. Okay, so we have to combine these. Now, you'll notice that I have 2 to the power of k plus 1 and another 2 to the power of k plus 1. Now, you know, in algebra, if you have x plus another x, that's the same as 2 times x, right? Or you have y plus y, it's 2y. Well, so if I've got one of these 2 to the power of k plus 1 and another 2 to the power of k plus 1, I could say it's 2 times the power of k plus 1. And of course, if you add the exponents here, this is to the first power, so you could add 1 plus 2 plus k plus 1, and you get k plus 2. All right? Now, k plus 2 could be written as k plus 1 plus 1 again, and that right there is what we wanted, because on the right side, if we want k plus 1 inserted for n, that's what we have already. 2 to the k plus 1 plus another 1 minus 1. And that's the k plus 1th term. Okay, that's the formula with k plus 1 added. That's not the k plus 1th term. 2 to the k plus 1 is the k plus 1th term. All right, so thus, we've shown that the sum from 1 up to the k plus 1th term is equal to the formula with k plus 1 stuck in it. So we've shown that it works for the k plus 1th term, assuming it works for the kth term. So by the principle of mathematical induction, putting the basis step together with the inductive step, we know it works for all integers from 0 on up to infinity. Okay? So mathematical induction is pretty powerful. All right? But we can also use it on things in computer science, including what are called recursive algorithms, and we'll talk about that. Now, example 4, page 318, gives a proof. It's a little bit more complicated proof, but it gives a proof of this formula right here. Now, this formula is the sum of a geometric series. A series is when you're adding up terms in a geometric sequence. So it's the summation from j equals 0 to n of ar to the j power. Now, of course, as j increases, you have terms that are the r is increasing in the exponent. In other words, we're multiplying by r to get the next higher term. So this is a geometric sequence, if you recall. And the formula is ar to the power of n plus 1 minus a over r minus 1. All right, now I don't know if you're familiar with such a formula, but that is the formula for the sum of a geometric series. Okay, and you can look at Rosen's proof of it. It uses mathematical induction on page 318. All right, example 6 says use mathematical induction to prove that 2 to the nth power is less than n factorial. Now, n factorial, if you recall, like for example, 5 factorial, that means 5 times 4 times 3 times 2 times 1, all the way down to 1. So this is proving that 2 to the power of n is less than n factorial for every integer n with n greater than or equal to 4. Now, it doesn't work for the first few numbers, but as soon as you reach 4, this works. Okay? And I'm going to show that here. The basis step says we start with showing that p of 4 holds. So that's our first starting number. But if you tried 3, well, 2 to the third power is 8. 8 is not less than 3 times 2 times 1, which is 6. 8 is not less than 6. But when you have 2 to the 4th power, that is going to be less than 4 factorial, and I'm showing it right now. 2 to the 4th would be 16, but 4 factorial would be 4 times 3 times 2 times 1, which is 24. And 16 is less than 24. So we've shown that it works for the when n is 4. Okay. Now the induction step says, let's assume it works for k, which is right here in yellow. 2 to the kth power is less than k factorial, and we're talking from 4 on up. So we have to show that it works for k plus 1. In other words, when n is k plus 1. All right? Now, how would we change the left side, 2 to the k, to be 2 to the k plus 1? Well, it's got increased, it has the exponent increased by 1, so that means we need to multiply by 2, okay, to increase the exponent by 1. All right, so that's what this says. We multiply 2 to the k is less than k factorial, the assumption in yellow, by 2. All right, so if you do that, you get what's in red here. 2 times 2 to the k is less than 2 times k factorial. So far, so good. And then, of course, we can add the exponents on the left side. So 1 plus k would give us 2 to the k plus 1th power. So the left side's taken care of. Now, the right side, though, what you have to use is the fact that 2 is less than k plus 1 as long as k is greater than 3. And we're only proving this for 4 and higher, right? So when k is 3, of course, 2 is less than 3 plus 1, or even when it's 4, of course, 2 is less than 4 plus 1. So as long as this is the case. Now, why did I want to use that? Well, look at what I have right here. I've got 2k factorial. But if 2 is less than k plus 1, then 2k factorial has got to be less than k plus 1 times k factorial. So in other words, it's because this coefficient, k plus 1, is higher than 2. So this term, k plus 1 times k factorial, must be greater than 2k factorial. In other words, 2k factorial is less than that. But what is k plus 1 times k factorial? Well, it equals k plus 1 factorial. Well, why is that? Well, I explained it right here. K plus 1 factorial, what does that mean? That means k plus 1 times k minus 1 times k minus 2. In other words, all the numbers below k plus 1 multiplied together, which isn't that the same as k plus 1 times k factorial? Because k factorial means all the numbers from k all the way down. So k plus 1 factorial is this k plus 1 times k factorial. All right? So now if you look at the left side and the right side of this big long equation or inequality, you have 2 to the k plus 1 is less than k plus 1 factorial. All right? So that means that we've shown it true for the k plus 1th term. And so if it works, we've shown the induction step that if it works for the kth term, then it's going to work for the k plus 1th term. And so now by the principle of mathematical induction, 2 to the nth power is less than n factorial for every integer k with n greater than or equal to 4. All right? So this one was a little different because it had the less than symbol and it used like factorial and exponents. So I'm just trying to help you to be ready to handle some of the things in the homework. So let's move on and look at the next one. All right. Now, Rosen gives a little template for doing a mathematical induction proof, because he wanted his students to write quality proofs. Um, I'm not gonna be real picky about the format aspect of the proofs, but I do expect to see the basics that are necessary. But step one, express the statement to be proven in the form for all n greater than b, and b will be your starting number. So it could be 0 or 1 or 4 like we did in the last time. P of n is true for a fixed integer b. Now write out the words basis step. So really announce that this is the basis step where you're showing it works for the initial values. All right. Then write out the words inductive step. So here you'll label what you're assuming. You're going to assume that P of k is true for some integer k. And then you state what needs to be proven. And what needs to be proven is that it works for k plus 1. So you might want to write out what P of k plus 1 says. In other words, like take the formula and instead of n, put in k plus 1. That's important because you need to know what your ultimate goal is in this step. Your ultimate goal is to have the formula with k plus 1 in it instead of n. Okay? Then, step 6, prove the statement P of k plus 1 making use of the assumption P of k. So using the assumption with the k in it in place of n, try to get from there using algebra to a step with k plus 1 inserted instead of n. Now you can't just insert it and say that's it. You have to arrive from the assumption with k to get to the step with k plus 1 by proper algebra. All right, so then step 7, clearly identify the conclusion of the inductive step, saying, this shows that, if it works for the k step, then it works for the k plus 1 step, which completes the inductive step. And then last of all, you say by the principle of mathematical induction, we know it holds true for all integers greater than that starting value. All right. Now, section 5.2 gives a little variation to mathematical induction. It introduces another method that's just a little bit different, and it's called strong mathematical induction. Okay? Well, it's called strong mathematical induction because it's more powerful or more usable for all different kinds of types of problems. So we can use it to solve more problems because it's more of a general approach. Now, strong induction says to prove that P of n is true for all positive integers n, where P of n is a propositional function, we complete 2 steps. So it's still the same thing that you have 2 steps. So we verify that the proposition P of 1 is true. So that's the same. You start off and show your basis step that it works for the first term. Right. Then we show that the conditional statement P1 and P2 and P3 all the way to PK. In other words, knowing all those ones prior to the k plus 1th term are true, all the values from the first all the way to the kth step. If you know those, then you will know the k plus 1th step. Right? So in parentheses here, it kind of explains what this is saying. So we have as assumptions that P is true for n equals 1, P is true for n equals 2, P is true for n equals 3, all the way till P is true for n equals k. So in other words, we have more assumption to go by. Instead of just assuming that it works for k, we can assume it works for K and all the values before K. All right? And then that's our assumption. All we have to show now is that it works for K plus 1 using all those assumptions. So if you look at our ladder analogy, it's saying we can reach the first rung, and for every integer K, if we can reach all the first K rungs, in other words, all the rungs below or from K on down, then we can reach the K plus 1th rung. So it not only gives us as an assumption that the Kth rung, that we can reach the Kth rung, but we can reach the Kth rung and all the rungs below that. All right, then we know that we've got to show that we can reach the next one after that. So it's a little bit stronger because we have more assumptions to start with, but it also is a valid induction or method of proof. Now here's an example that Rosen gives using stamps. It's on page 337. So example 4, prove that every amount of postage of 12 cents or more can be formed using just 4 cents and 5 cent stamps. Okay, now I'm going to look at, this is the regular mathematical induction, but then after that we're going to look at the strong induction. All right, so solution, we will prove this result using the principle of mathematical induction. Then we will present a proof using strong induction. All right, so this page is the regular math induction. So we begin by the basis step. Now you start with 12 cents. That's your basis amount. Show that 12 cents can be formed. Well, if I just take 3 of the 4 cent stamps, I can make postage for 12 cents. So that's done. We're done. We just had to show it works for the first step. Okay. Now the inductive step, the inductive hypothesis is the statement that P of K is true. Now, we are assuming that we can make postage of K cents using 4 cents and 5 cent stamps. Now, to complete this step, we need to show that when we assume P of K is true, then that P of K plus 1 is true, as long as K is greater than or equal to 12. Now, so basically, that if we can make postage for K cents, that we can make postage for K plus 1 cents. Now, if we can make postage with these 4 and 5 cent stamps for the K amount, then we must have used 4 cent or 5 cent stamps. Now, there's two cases. Either we used at least one 4 cent stamp, or we did not use any 4 cent stamps. Now, in the first case, if we used a 4 cent stamp, we could just take that 4 cent stamp away and add a 5 cent stamp. And now we've gotten K plus 1 from K. All right, if K cent stamp or K cents was arrived at using a 4 cent stamp, all we have to do is remove the 4 cent stamp and replace it with a 5 cent stamp, and now we have K plus 1 postage. Okay, but if we didn't use a 4 cent stamp, in other words, we used just 3 cent stamps, or I'm sorry, just 5 cent stamps, okay, if K is greater than 12, then we must have used, 3 5 cent stamps if we didn't use any 4 cent stamps. Okay, well, 3 5 cent stamps is 15, right? So if we I mean, to reach a postage above 12 with or equal to 12, we had to use, and if we didn't use any 4-cent stamps, we had to use a lot of 5-cent stamps, at least 3 5-cent stamps. Okay, so all you have to do is take away those 3 5-cent stamps and replace it with 4 4-cent stamps, because 4 4-cent stamps is 16. And if I replace 15 cents worth of postage with 16 cents worth of postage, then we've reached the one higher. In other words, the K plus 1 amount of postage. Okay, so that's how it was done with regular mathematical induction. But we had that sticky case of, what if we didn't use any 4-cent stamps? Well, you have to know that if it's a postage higher than 12, which the first one would be 15, that you could get with 5-cent stamps, well, then you have at least 3 of the 5-cent stamps that can be replaced with 4 of the 4-cent stamps to give you 1 higher cent of postage. Anyway, but by the principle of mathematical induction, then we could reach all postages over 12 cents. Now, the strong induction would work a little bit differently. Look at the basis step for this. So we could form postage of 12, 13, 14, and 15 cents using 3 4-cent stamps. So that'll give you your 12. Or 2 4-cent stamps and 1 5-cent stamp. That'll give you 13. Or one 4-cent stamp and 2 5-cent stamps. That'll give you 14 cents. And then 3 5-cent stamps respectively. That'll give you 15 cents. So we had to show it worked for all of those, but that completes the basis step. Now you'll understand in a minute why we had to show all of those. All right, now the inductive step says, is the statement that P of J is true for all the values from K on down. Okay, K on down. So we have all that more to go with. All right. Now, in that case, if we know that it works from K on down, so then it must be that it works for P of K minus 3, because isn't K minus 3 is less than K, and we know it works for all of those values before K and including K, so it works for K minus 3. Well, then all you have to do is add 1 4-cent stamp, because 4 added with K minus 3 gives you K plus 1 cents. So we have just shown that it works for K plus 1 using the fact that it worked for K minus 3. So you may have wondered, why did we have to go and in the basis step show it works for 12 and 13 and 14 and 15? Well, that's because we referenced P of K minus 3. So we had to show it worked for 15 because we're to show from there on up to the 16th one, it referenced K minus 3. So what's 3 less than 15? Well, it drops it down to 12. Okay, and that would be used for proving it works for 16. And then from 16 to 17, what's 3 less than 16? Well, it's 13. So it would reference this 13 one. And the same thing with if you're trying to go from 17 to 18. What's 3 less than 17? It's 14. And then for going from 18 to 19, what's 3 less than 18 is 15. And then after that, you already have shown it worked for the 16, 17, 18, so you can just keep going forever. So that's why that works. So the proof ends with saying, okay, we've shown that it works for the first few cases, 12, 13, 14, and 15. And we've shown that if it works for any case, then it works for the next case. So that means that we can make any amount of postage using just 4-cent and 5-cent stamps from 12 cents on up. Now, the principle of mathematical induction can be applied to geometric figures, including graphics. So computational geometry is what we call discrete math applied to geometric elements, such as polygons or trees. Now, we don't have the time to study trees in this class, but you can read up on trees on page 351. Trees are objects in computer graphics. But we're going to apply it to geometric polygons, first of all. So a polygon is a closed figure with whose sides are line segments, S1, S2, S3. So I show a picture of a polygon here with line segments S1, S2, S3, S4, and S5. But it could have as many sides as you want. Such that every two consecutive sides, Sj and Sj plus 1, as well as the first side, S1, and the last side, in this case S5, share a common endpoint called the vertex. Now you'll notice that S1 and S2 share the common vertex right here. S2 and S3 share this common vertex. All right, so there's a common vertex that is shared by any two consecutive sides. Now, a simple polygon is one where no two non-consecutive sides intersect. Okay, now a non-simple, picture an hourglass, like you go this, 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 this. So that kind of thing where they cross in the middle, the two segments cross in the middle, that's not a simple polygon. A simple polygon cannot cross in the middle, right? And so this is a simple polygon. This pentagon here is a simple polygon, right? And it separates the plane into the interior and the exterior. Now, this is also called convex because it doesn't bend inward like the next one. This is non-convex, or also called concave. But anyway, the definition of convex means that every line segment connecting two vertices of the polygon lies entirely inside the polygon. Now, if it's not convex, we call it non-convex. Now, a diagonal is a line segment connecting non-consecutive vertices. So what we're talking about here is diagonals. If you, in this convex one, if you draw a diagonal, it always stays inside the polygon. All right, so we call that convex. But in the second case, this is non-convex because this diagonal right here did not stay inside the polygon. All right, so there's some terminology that we are going to use. All right, so an application of induction, strong induction, can be made to computational geometry in the area of triangulating a polygon. Now, triangulating a polygon means dividing the polygon up into triangles by drawing the diagonals of the polygon. And theorem 1 is what we're going to look at, the proof for. It says a simple polygon with n sides where n is greater than or equal to 3, can be triangulated into n minus 2 triangles. Okay, so the proof is using strong induction, stating that if a polygon has k sides, then it can be divided into k minus 2 triangles, okay, which is the inductive hypothesis, that it works for k. So k is being replaced with n here, so it's going to be able to be divided into k minus 2 triangles. Now we also need to establish the basis step, so if n is 3, the figure is already 3 minus 2 or 1 triangle. So obviously if you have a 3-sided polygon, that's already 2 less than that, or 1 triangle. Now consider a polygon P as shown in the picture with k plus 1 sides. So we're imagining or we're considering the case where it has k plus 1 sides. So we have to show that that would mean that it has 2 less than that triangles that you could divide it into. All right, so if P has k plus 1 sides, I could draw a diagonal, and then it divides the polygon into 2 other polygons. Now, R doesn't have to necessarily, like in the picture, R does not have to be a triangle. It could be another polygon, just like Q is another polygon. All right, so let's suppose that when you divide P into those 2 polygons, Q and R, that Q has S sides and R has T sides. Okay, and we know that S would have to be somewhere between 3 and K. And then T would also have to be somewhere between 3 and K sides. Because it has to be that, you have a couple sides from the other polygon, and so you're going to definitely have less than or equal to K sides. Now, each side of P will either become a side of Q, so like this side right here is becoming a side of Q, or it's becoming a side of R, but it's not going to become a side of both of them. And the diagonal is going to be a side of both of Q and R. So that means this polygon with k plus 1 sides is going to have S plus T minus 2 sides. Okay? Because it's like S minus 1, S minus, or T minus 1 added up, because this one side is not being counted in it, in the original k plus 1 sides. So now, by the induction hypothesis, we can divide Q. Now, the induction hypothesis is where we know that if it has S sides, that it's going to have S minus 2 sides. And the same thing with T. If it has T sides, it's going to have S minus 2 triangles. And if it has T sides, it's going to have T minus 2 triangles that you could divide, that it'll divide up into. All right. So that's using the induction assumption or hypothesis. Now, P with its k plus 1 sides then can be divided up into the sum of those two expressions, S minus 2 plus T minus 2 triangles, okay, because Q can be divided into S minus 2 triangles and R into S or T minus 2 triangles. So the number of triangles, not sides, but triangles that would be all of the polygon P is the sum of those two, which if you add these two expressions, you get S plus T minus 4. But we already had up here that S plus T minus 2 is equal to K plus 1. So I can replace this s plus t minus 2 with k plus 1, and that gives us that the whole polygon has k plus 1 minus 2 triangles. Well, we have just shown then that if it has k plus 1 sides, then it's going to have k plus 1 minus 2 triangles. Now, we're just trying to illustrate the principle of mathematical induction, strong induction. So this is a pretty tough example for you to come up with on your own, and it's even tough for me to think about on my own. So I'm not expecting you to necessarily do that, but maybe just answer questions about it or try to understand it for this purpose. All right, but you might be able to do some application of strong induction on some geometry type situation. So that is the principle of math induction and strong induction, which really are two different sides of the same coin. So give it a try in the homework and see how you can do. All right.